In this video, we present our work, Automatic Gait Pattern Selection for Legged Robots. To motivate our work, let us consider legged animals in nature. When legged animals move, they decide an appropriate gait pattern for a given task and environment. The gait pattern refers to the sequence in which the feet make and break contacts with environment. On the flat ground, the selection of gait pattern is often influenced by desired locomotion speed. However, when facing challenging terrains, gait pattern selection becomes more complex. Due to the need of ensuring a feasible motion, legged animals need to carefully select the contact sequence. Usually, these contact sequences are acyclic and arbitrary, and have to adapt according to different terrain conditions. Similarly, legged robots face the same challenge in unknown industrial environments. When there are terrain irregularities, cyclic gated motions might be no longer valid. The robot has to solve a hard combinatorial problem to select an appropriate gait pattern along with a feasible motion. Although we can try out all possible combinations, it is computationally expensive. A common workaround is to rely on expert knowledge to determine a gait pattern for a given situation. For instance, the video shows a field trial of our animal robot, where a human operator is supervising the gait pattern selection. When moving on the flat ground, the human operator chooses the trotting gait to achieve fast locomotion speed. When there are terrain irregularities, a more conservative gait pattern, static walking, is selected to increase robustness. However, relying on a human for gait pattern selection can be tedious and difficult. In this work, we propose the idea of using an automated framework to build a map from task conditions to optimal gait pattern selection. During online operation, the robot can query the map to quickly get the right gait pattern. To generate the map, we first use a mixed integer optimal control formulation to generating a dataset. This dataset contains task samples and corresponding gait patterns. Next, we use a neural network to capture the structure of the map in the form of gait regions. To give more detail of our approach, we focus on introducing our mixed integer optimal control formulation. Given a task descriptor, kappa task, our formulation aims to compute a, n phase motion that minimize a user-defined cost j. In this work, we consider periodic locomotion tasks where we use v and t to denote forward locomotion speed and cycle duration, respectively. The decision variables of our formulation includes pi, a collection of continuous trajectories such as body trajectory, gamma, feet trajectory, p, and contact force profile, f. The gait pattern matrix, lambda, which uses binary variables to denote the contact configuration of each phase. And phase switching time vector, tilde t. To ensure the motion is physically consistent, we enforce task constraint to fix the initial and terminal robot configuration according to the task descriptor. Switching time constraint to ensure they increase monotonically. Dynamics constraint where we use a single rigid body model with mass-less limbs to describe the robot dynamics. Kinematics constraint that uses a box to approximate the feet reachability. Friction cone constraint to prevent feet sliding. Contact dynamics constraint. The contact dynamics constraint can be seen as a mixed integer formulation of the complementarity condition. In each phase, we enforce unilateral contact forces that can only push from the ground, and the feet should not penetrate into the ground. When a feet is not staying in contact, the contact force should be zero. If a feet is in contact, the distance between the feet and the ground should be zero, and the feet velocity should be zero as well. To solve the optimal control problem numerically, we introduce a variable time step parameterization scheme, in which we put same number of knot in each phase, and the time interval covered by each knot scales proportionally with respect to the change of phase switching time. The resultant mixed integer optimization problem is then solved by the branch and bound algorithm, which systematically explores the motions characterized by different gait patterns. In fact, we are not the first to apply mixed integer programming for legged locomotion planning. Recently, IROS2020 has proposed a mixed integer convex programming formulation for generating the motion of legged robots. In their work, the authors use a single binary value to represent the entire foot swing phase, which can only model symmetric gait patterns that have synchronized breaking of contacts, such as walking and trotting. Further, a convex centroidal dynamics model is employed, but it cannot properly encode the typical changes of the angular momentum during highly dynamic motions. Lastly, the phase duration is fixed to avoid bilinear constraints, but restricts the search space. In contrast, our formulation solves the aforementioned problems, with the cost of ending up with a nonlinear optimization problem. More specifically, as our gait pattern matrix uses binary variables to represent the contact configuration of each phase, our formulation can model both asymmetric and symmetric gait patterns. Also, we use a nonlinear model to accurately describe the angular dynamics. To explore a wide range of motions, we optimize the phase duration. For more information of our formulation, please refer to the methods section of our paper. Next, we present the result of our work by starting from a 2D half-cheetah model. The figure on the left illustrates the optimized gait patterns for a set of periodical locomotion tasks on a flat terrain, with the cost of minimizing contact forces. From the figure, we can observe that distinct gait patterns tend to occupy contiguous regions whose boundaries can be easily captured by supervised learning algorithms. For instance, at very low speeds, the model favors walking gaits. If we increase the speed, the model prefers to gallop, as shown in the video. Note, we have mapped the motion by synchronizing front and hind limbs of a 2D quadruped model, respectively. When it comes to large cycle durations and speeds near the maximum, the bounding gait becomes favored. The pronking gait and gallop-bound gait cover two small regions during the transitions from gallop-walk to gallop, and gallop to bounding. Similarly, when we switch the cost to minimize trunk vibration, we can still observe the structural property. However, the distribution of the gait regions becomes significantly different. For medium velocities and across the entire cycle duration range, the bounding gait is preferred, as shown in the video. Also, we can observe an increase of the gallop-bound gait region during the transition from gallop gait to bounding gait. Additionally, the gallop-walk gait becomes prevalent at the low-speed regime. Next, we explore the effect of changing terrain inclination to 20 degrees. Again, although the structural property is preserved, the region covered by each gait pattern has been mostly changed. For instance, same as the flat terrain case, at the low-speed regime, the model prefers the gallop-walk gait as the video demonstrates. However, for low cycle duration and medium velocity, the gallop gait becomes favored instead of the bounding gait. Furthermore, we can observe the pronking gait, gallop-bound gait, gallop-pronk gait, appear to cover small regions during the transition from gallop to bounding. The result of the 2D half-cheetah model suggests that human intuition might fail to capture the complexity of gait pattern selection, which is highly dependent on the task conditions, desired performance objective and environment. We further extend our study to the 3D quadruped robot animal. To generate a wide range of possible motions, we allow large contact forces and foot velocity. To alleviate the combinatorial complexity, we set the number of phases to be 4, which gives us totally 65,536 candidate gait patterns. The figure on the left illustrates the optimized gait patterns for the 3D case. Again, we can observe a structured pattern in the map. For low speeds, the robot favors a series of gait patterns that avoid flying phase. In higher speed regimes, the robot transits to gait patterns with noticeable flying phases, such as running trot and pace. Next, we demonstrate a couple of motions for the 3D case. Gait 6, running trot, and Gait 5, 4-beat walking. Gait 2, walking trot, and Gait 1, 3-beat walking. Additionally, we find the state trajectories within each gait region are qualitatively similar. To better illustrate this point, we plot two examples, the state space trajectories for the gallop-walk gait of the 2D half-cheetah model, and the trajectories for the running trot gait of the 3D quadruped. The horizontal axis represents the height of the center of mass, z, the vertical axis refers to the pitch angle of the body, theta. In each of these two regions, the state trajectories share a similar shape but have different sizes. It seems that each gait region has its own basin of attraction. This encourages us to utilize this fact to construct initial seeds to warm start our optimal control problem, such that we can achieve fast computation speed. In this work, we build the initial seeds for each gait region by taking the mean of the sampled trajectories. We take the 3D quadruped as an example to highlight the benefit of using the constructed initial seeds. For a couple of randomly sampled task descriptors, we firstly use our mixed integer nonlinear programming approach to compute the optimal motions as a baseline. Due to the combinatorial complexity, the average computation time is about 5 hours. For the same set of task descriptors, we use the gait pattern selection map to pre-define the gait pattern for our trajectory optimization problem, and give random initialization to the state trajectories. As expected, the computation time drops to 19 seconds since the combinatorial complexity is removed. However, since the trajectory optimization problem is still nonlinear and non-convex, some of the trials fail to converge to a local minimum, or converge to a different local minimum in comparison to the result of our mixed integer approach. When we utilize the gait pattern map and constructed initial seed together, the computation time becomes 300 milliseconds. And all the trials have successfully converged to a local minimum, and are consistent with respect to the result of our mixed integer approach. To validate our approach, we adapted the model parameters to be close to the capability of the robot, and we performed a real-world trial for a motion generated by our framework. To conclude our work, we propose the idea of building gait pattern selection maps using mixed integer optimal control and supervised learning. We show that discovered gait maps exhibit structural properties, and the trajectories in contiguous gait region are similar. We exploit these properties to speed up the computation by warm starting. Thank you for watching.